is do this second lesson, get done by 11 o'clock, and then let you work for a while, and maybe sometime, hopefully, sometime this afternoon, I'll teach again. For each of the following functions, state the end behavior and equations of all the asymptotes. This is a review of Chapter 4 and 5 of advanced functions coming up, or the important features of Chapter 4 and 5. Way back here, end behavior of functions of polynomials was just this. Well, I didn't get to do the dance in class because you were on coronavirus break, but that's all that was going on here. And to review that, why that's true is, if I sub in a really big number, say x equals 1,000, the only number that's going to matter, like 8, isn't going to matter. If I'm subbing in 1,000, 8 doesn't really matter. Even the 6 doesn't matter. That's like 6,000. X squared, that's like 7 million. That seems big, right? It's like, oh, that matters. No. Negative 4 billion right here. So as x goes to infinity, this function has to go to negative infinity. And all the information about that is in that leading coefficient. The fact that it's a negative leading coefficient means that this has to go to negative infinity. What happens though if I sub in a big negative number? When I sub in a big negative number in for x cubed, like negative 1,000, I'm going to get like negative 1 billion. But then it gets multiplied by a negative, and the function goes to positive infinity. Does this ring a bell? I know, see, when we do this in class, I totally do the dance with you and everything like this, and you get to see it all, and it really gets entrenched because of the nonsense of me dancing up here. But does this ring a bell that you had to write these things for polynomials? Okay, so for polynomials, it's pretty straightforward. The only possibilities are, here's the review. Positive even degree. It's up on both sides. That's like x squared, right? Up both sides. Negative even degree. Down both sides. Positive odd degree. Positive still goes up, but the negative side goes down, and then negative odd degree.
Sorry for the interruption. Angela Rose, please go to the library now. Angela Rose, to the library now.
Tell me now if this isn't beautiful review. Like if it's like, I'm not sure I'm not sure what you're talking about. We're just talking about end behavior here, what we do at the ends of polynomials. So use that for this one. As you go to infinity here, what's going to happen to this function that has an even degree? You can go back to x squared. What happens with x squared when you have positive coefficients? Up both sides. So this one does the same thing. As 7x to the fourth, we get, and I used y here instead. It really doesn't matter if you use f at x or y here. Is that good or no? I can't read you. I don't know if I've lulled you to sleep or whether you're confused and don't want to admit it. Is this good? 3 thumbs up. Somebody opened their eyes for a second. That was good? Okay, yeah, so we're good here. Not particularly difficult situation. In fact, you can actually figure this out just by subbing a big number in. If you sub in 1,000, you're going to get 7 billion. The function is going to go like this as it goes off to infinity. More time here? As the x goes out here, the y value is going to be going straight down like this. So all those polynomials, before rational functions came along, all the polynomials did this and then either ended up like this or like this at the ends. They went off to infinity or negative infinity on either side. So this is just saying the rules about what you're going to see there. Negative odd degree, right, yeah. Are we good? Fast forward to rational functions. And at that point, what we were really looking for was horizontal asymptotes. We had a set of rules about horizontal asymptotes. But let me develop the rules. I've got to 11, so I want to make sure I don't really skip anything here. Let's say I subbed in 1,000 into this. If I did sub into 1,000, the top would come out to 6 million something. There'd be extra little pieces here, but really it's around 6 million. The bottom would come out to around 2 million. Close to 2 million. What's 6 million divided by 2 million? The number 3. As x goes to infinity, this function goes to the ratio of the coefficients. Is that ringing a bell from chapter 5 online? Here was the rule in the notes for advanced functions. If the degree are equal, you have a horizontal asymptote at y equals ratio of leading coefficients. So even if that's not still in your brain from Corona advanced functions, there's the rule when you've got a rational function. The rule went farther. It said if the degree was higher on the top, we'd get no horizontal asymptote. Better yet, limit as x goes to infinity of g at x would equal infinity. And I put that infinity in quotes to say, well, some people don't like that limits can equal infinity, so I say, oh, it heads to infinity. Do you have questions? I'm certainly not trying to present this as easy because it either is there in your brain from advanced functions or it's really not. So I'm happy to explain more if you want. Sorry? Oh, yeah. I should have put a limit as x approaches infinity there. This is a limit. Where's the head towards 3 as we go to infinity? Basically what we're saying is the top's going to be like 600 million, the bottom's going to be like 200 million, and when you divide those two, it just is going to head towards 3. Let me just draw a graph that might ring some bells. We're doing stuff like this in advanced functions. It heads towards 3. Its limit as x approaches infinity heads towards 3. Tell me now. I don't care about this 11 o'clock deadline. I'll do this in 2 parts if this needs more explanation. More? More. Let's talk about subbing numbers in. Big numbers. That's all we're talking about because this is all, remember, this lesson is called Limits Involving Infinity. And it asks me, when I go back to the regular lesson, it says, for each of the following, state the end behavior, which means find out what's happening at the ends of this thing. So when I look at this function, and let's say I want to know end behavior, what's happening out at the ends. So one thing I could do is sub in a big number. F at 1,000. There's a pretty big number. That's going to tell me what's happening out at the end of this function. So I'm going to type that into my calculator. 1,000 plus 4 divided by 1,000 squared minus 5 times 1,000 plus 9. I close the bracket. And I get, look at this, 0.001009036. And what those rules that I'm talking about did in advanced functions was give you a shortcut to not having to sub in every time. There's a way to look at this function and know that you were going to get close to 0 by just looking at the degree of the function at the top and bottom. So without doing all the subbing, I'm going to talk about what happens if I sub in x equals 1,000. Look at the numerator there. The numerator is going to be 1,000 plus 4. That's a pretty big number. 1,004. This function is going to be huge. Then I look at the bottom, and there's an x squared there. Now, squaring big numbers does really big things to them. Just think about that for a second. Let's talk about 1,000 for a second. If I handed you $1,000, you'd be dancing in the street. 1,000 is a really big number until 1,000 squared comes along. Just imagine that for a second. If I said I gave you 1,000, you'd have the biggest smile on your face ever, and I said to you, okay, take your $1,000 and burn it. You're like, no way I'm burning my $1,000. Okay, but here's the deal. If you burn the 1,000, I'll give you $1 million. Well, of course you'll burn it. $1 million is way more than 1,000. Like it's like 1,000 thousands. It's 1,000. It's 1,000 every day for 3 years. That's how big $1 million is. So what happens here is the numerator comes out to around 1,000. The denominator comes out to around $1 million, and when you divide, it becomes really small. And we get the first of the 3 degree rules. If the degree of the denominator is larger, limit as x approaches infinity of f at x will head to 0. This thing's going to head to 0. And in advanced functions, you would have said horizontal asymptote at y equals 0. So now that slide reviews advanced functions, horizontal asymptotes, or one of the rules, because there was 3 rules, and brings it into AP Calc to say, well, we're going to call it a limit. What's the limit as we head out to infinity? Does that help to understand what I'm trying to accomplish here with the degree rules? Okay? That's one of the 3 rules. So I'll label that. If you're like, oh, I don't remember these at all, there's rule number 1. And it talks about if the degree of the denominator is larger. I'll give you time to get that down, and then I'll go back to the previous examples and frame them into this set of rules from advanced functions. You see, you can just sub in a number, by the way. Sub in 1,000, you'll get the answer. We're just trying to come up with a faster way to do it than having to sub into these crazy functions. And those rules are going to help when we're going to do more complicated things this year. More time here. More time here? Okay, back to the examples I was doing. Start over again. If it's not a rational function, you don't have these problems. Subbing in a big number here, like 1,000, you know what you're going to get. Negative 4 million. Sub in negative 1,000, you're going to get positive 4 million. So things aren't complicated with polynomials. But when you get to these ones, let's talk about subbing into 1,000 into this. 6 million and a bit. 2 million and a bit. That's where this rule comes from. This is rule number 2. If the degrees are equal, you're going to get your horizontal asymptote. And it's going to be at y equals the ratio of the leading coefficients. Getting better? We're getting better? Question? Say it again? Oh, good. She wants to know, how is the end behavior related to the limit? Beautiful. I'm going to draw a picture. I'll go back to my other slide here. So, if I were to draw this thing, I don't know much about it at this point. I'd have to do a lot more research. I'd have to find, here comes the list from advanced functions. I'd have to find the x-intercepts, the y-intercepts, the vertical asymptotes, all those things, and I put them all together to come up with a graph. All I've really discovered about the graph is, this particular graph, is that this function has a horizontal asymptote at y equals 0, which means if I were to draw it, I don't know what it does, but it's going to head to 0 as it goes out there. Sort of like an exponential does, but it does it on both sides. And I don't know if it goes on the negative side or the positive side. I'll have to do more work to figure that out. But it's got a horizontal asymptote at y equals 0. That's the same as saying limit as x goes to infinity of f at x is 0. See, the horizontal asymptote is where it's headed towards. That's what we were talking about the whole time. Actually, we didn't know it. We called it a horizontal asymptote, but we were talking about the limit as x goes to infinity. As the x goes to infinity, where is it heading towards? 0. And see how the heading towards takes care of the fact that it never gets there. In the limit, we're not worried about if it gets there. We're worried about where does it head towards. Does that help relate the two? The limit is the horizontal asymptote. Okay? Let me do another one. I'm switching my plan. I'm doing this lesson in 2 parts. We're going to wrap it up at your normal break time, which is what, 10:30? We'll get back together and I'll continue on. And the people that have to go will have to watch the video later or see me later. Let's talk about this one. In advanced functions, we would have said that the horizontal asymptote is the ratio of the leading coefficients. And we would have found that this graph approaches 3 on either side. It has a horizontal asymptote at y equals 3. We didn't know it. We were talking about limits. The limit as x goes out to infinity is 3. It's heading towards the number 3. And here it's heading towards the number 3 as you go over here. So that's the second of the 3 rules. A little better? Okay, good. The third of the 3 rules. What happens if the denominator's the bigger one? As x goes to infinity, there's no horizontal asymptote. The limit goes to infinity, so if I was to draw this graph, I don't know exactly what it looks like. I take that back. I sort of know what it's going to look like, but I don't think at this point in the lesson that you should know what it looks like, is that this function is going to go off like this in either direction. It actually has an oblique asymptote, which I might have completely just skipped over when we were online. The important thing is when the third rule, here it is, let me write it over here, 3. If degree of numerator is bigger, no horizontal asymptote. Does that cover all 3 cases? There's only 3 cases. Numerator bigger degree, denominator bigger degree, degrees equal. And we'll leave oblique out of the conversation for now, because that is a separate conversation really. It was done separately in advanced functions. How are we now? Better? And so this limit would head off to infinity. Notice though that this thing said equations of all asymptotes. Polynomials don't have asymptotes. Rational functions can have horizontal asymptotes. What other kind of asymptotes can they have? We done horizontal? What's the other one? Vertical. Vertical easier to find and understand. In grade 11, we just called these restrictions. And then in advanced functions, we were to discover that those are actually vertical asymptotes. It means there's this straight line, straight up vertically, that this function heads towards but never reaches. There's some limit implications here that I won't get carried away with just yet. But all we're saying is that that function can't exist there. And not existing, you have several choices. You could have a hole, or you could have these vertical asymptotes. What about this one? What's the vertical asymptote here? I don't need to do any factoring this time. -2. It was called the restriction in grade 11. X can't equal -2. And in advanced functions, we were supposed to go, yeah, I know, x can't equal -2 because there's this vertical asymptote here that this function cannot cross. Questions? All right, let's do it all from the top. All the vertical asymptotes and horizontal asymptotes and limits all in one question. So now we'll check. Is it all coming together for you? Let's talk about horizontal asymptote first. And we do horizontal asymptote. All we're thinking is, what happens as x gets really big here? And we've got our 3 rules available. First rule. Denominator is bigger. And what happens if the denominator is bigger? Goes to 0. So the horizontal asymptote here is y equals 0. I get those right from the rules. If you don't like the rules or you don't remember the rules, I got a new trick to show you. It's an awesome algebraic trick. It's going to allow you to find these things. I'll use it for this one after the break. I'm going to finish this up, and then that's when we're going to take our break. What's the other thing they wanted? Vertical asymptote? How do I go about finding vertical asymptotes? Just factor the denominator. So here it's 3 minus 4x over x plus 3, x plus 4. So my vertical asymptotes, x can't equal -3 or -4. And then what they were really asking was limit as x approaches infinity of 3 minus 4x over x squared plus 7x plus 12. And that limit is 0 because that's what the horizontal asymptote is. After the break, I'll pick it up there and show you a smoother way than the rules to find those answers that will be very helpful to us. Any questions though before our break? Please notice, as soon as I sensed that this wasn't going well, because for whatever reason, I don't care anymore what happened in Unit 5 and why it's not, just because the way it was taught, or whether you got the answers from somebody else, or whatever happened. I don't care anymore, but I need to know. Yeah? I'm like your doctor of mathematics here. You've got to tell me what's going on, or I'll just cruise right along. I could have easily right there. I came within moments of just cruising right through this lesson, going, oh yeah, you remember from advanced functions, remember this, remember that. And you're like, no, we don't remember. Tell us more. It's the only way we're going to survive this, is if you keep telling me. There is no, oh, I don't want to appear like I don't know. I don't want to appear like I cheated in advanced functions. I didn't cheat. I did cheat. It doesn't matter to me. It's irrelevant to me what happened during coronavirus. All that matters is, do you understand what I'm saying right here? And if you don't, you got to come up with a signal system. You want to just put a thumbs down up there and you just want to shake your head? One of my favorite students ever used to sit right there. Moved her desk and sat right there, and she would sit there during my lessons and just shake her head. She'd just go. And it was great. At least I knew. Go again. Show me again. Okay? So make sure you're letting me know. Okay? We're going to take the time. I'm going to keep pushing. I got to. I got to try and finish this course. But when we need the moments, we'll take them.